A 2.4 kilogram box is placed on an inclined plane of inclination 37 degrees. If the coefficient of kinetic friction between the box and the plane is 0.3, what is the minimum force required to move the box up the plane with a uniform velocity? And what is the minimum force required to keep the box from moving down if mu s equal to 0.5? Well, I know you will say this has nothing to do with conservation of energy. Well, that is true. This is something that we did earlier. So this is a problem purely on friction. I want to do it anyway. Okay, we have an inclined plane of inclination 37 degrees, and you have a box of mass 2.4 kilogram on the inclined plane. Now let's look at the forces on this box. This is just a review from the 2 lessons, is that right? 2 lessons away. What are the forces acting on the box? The weight of the box equal to mg. M is 2.4 kilogram, g is 9.8 meter per second squared. So the weight is 23.5 Newton acting vertically down. Alright, can you tell me the other forces? What is the component that is pulling the box down the plane? The component of this force pulling the box down the plane is mg sine theta, mg sine 37. mg is 23.5 Newton, so that will be 23.5 sine 37, and that is 14.1 Newton. That is the force pulling the box down the plane. Well, what is the force acting up the plane? If the box is going to slide down, then the friction is going to act up the plane. The force of kinetic friction is, do you remember? What is the equation for force of kinetic friction? Well, the box is sliding down, is that right? If the box is sliding down, then the friction is the force of kinetic friction. Fk is mu k Fn, mu k times the normal force. What is the normal force pressing the 2 surfaces together? That will be mg cos theta. So the force of kinetic friction will be Fk equal to mu k mg cos 37 degrees, which is mu k is 0.3, mg is 23.5, we know that, times cos 37, and that is 5.6 Newton. Now the question is, in what direction is that frictional force acting? Well, friction always opposes motion. So the direction of the frictional force is opposite to the direction of motion. What does the A part say? What is the minimum force required to move the box up the plane with a uniform velocity? I want to move this box up the plane. So in what direction will the friction be acting? If you want to move the box up the plane, the friction is now going to act down the plane. And now, you don't want to create an acceleration on the box, do you? No. We don't want a net force. We want to balance the force. That's all we want. Because what we want is, we want to move the box up the plane with a uniform velocity. When the box moves with uniform velocity, there is no net force on the box. That means the total downward force needs to be overcome by an upward force. so that the net force is 0. Alright, when you move the box up the plane, what are the downward forces? Well, mg sine theta always acts down the plane. That will be always downward. And now, because you are moving the box up the plane, this frictional force Fk equal to 5.6 Newton is also acting down the plane. It is opposing the upward motion. So the total force now acting down the plane is 14.1 plus 5.6. And in order to balance that, you need to apply the same amount of force upward. Alright? Since we want to move the box up, the frictional force Fk acts down the plane opposing the upward motion. So the frictional force Fk equal to 5.6 Newton is also down the plane for this part of the problem. And therefore, what is the minimum force that you now need to apply upward? The minimum force must therefore balance these two downward forces. So that F minimum therefore must be equal to 14.1 Newton plus 5.6 Newton, that is 19.7 Newton. A force of 19.7 Newton applied upward will make the box move uniformly without an acceleration. There is no net force on the box at that time. Alright, how about B part? What is the minimum force required to keep the box from moving down? This time, the box is not going to move. We need to keep it from moving down. That means the force of friction will be static friction. Alright, tell me, we are now trying to prevent the box from moving down. That means the tendency of the box is to move down. If the box has a tendency to move down, the friction will oppose that. So this time, the friction will be opposing that tendency to move down. And the frictional force this time is the force of static friction, which is mu s mg cos theta, mu s mg cos 37 degrees. Mu s is given to be 0.5, mg is 23.5 Newton times cos 37, and that is 9.4 Newton. So when you place this block on the inclined plane, this frictional force is preventing it from sliding down. But because the downward force is 14.1 Newton, this frictional force alone will not keep it there. You need an additional upward force to prevent it from sliding down. The question here is, what is that additional force? When the box tends to slide down, I know many of you have problem understanding this concept. I have seen it in my class before. When the box tends to slide down, the force of static friction is acting up the plane. Is that right? When you place the box on the inclined plane, the box wants to slide down under this force, 14.1 Newton. And the friction is going to prevent it. So the friction is going to act up the plane. Now, so we have a frictional force, force of static friction, that is 9.4 Newton acting up the plane. The force of static friction Fs now assists the applied force F minimum to prevent the block from sliding. That means if you now want to keep the box from sliding down, we need to balance the downward force with the upward force. So the F minimum added to the frictional force must balance the 14.1 Newton down the plane. So you're going to apply an F minimum, that is the green arrow here, upward, and the sum of the red arrow and the green arrow upward must balance 14.1 downward. So we say F minimum plus 9.4 Newton equal to 14.1 Newton, and that gives you the F minimum as 14.1 minus 9.4, that is 4.7 Newton. Okay, let's now go back